All right, thanks for watching. And today we will solve a PDE in a ball because, as Queen once sang, we're having a good time, we're having a ball. Okay, more precisely, consider the ball centered at 0 and radius 1 in Rn, or if it makes it easier, in R2. So again, B01, the open unit ball. And what we would like to do, we would like to solve the following PDE. Namely, we would like to solve Laplace's equation. So Laplacian of u equals 0 in the open unit ball, and u equals to some fixed function g on the boundary. So what is happening inside in the unit ball, u is harmonic, but on the sphere, u is equal to some fixed function g. And how do we solve this? Well, the beautiful thing is this is yet another application of Green's function, but this time with a more clever reflection technique. And for this, let me remind you a little bit about Green's functions. And by the way, you can find a more thorough treatment in the playlist. And for this, first of all, let me recall the fundamental solution of Laplace's equation. So phi of x equals some constant times 1 over length of x to the n minus 2. And that constant here we'll need is n times n minus 2 alpha n, where n is a dimension, alpha n is the volume of the unit ball. Okay, now how does Green's function work? So step 1, first of all, fix some point in that ball. Okay. So again, you have this ball and you fix some point x, and then what we would like to do, we want to find a helper function. So we want to find some function phi. Again, x is fixed, so it's really a function of y. That is a solution of the following helper PDE, namely, phi x is harmonic, so minus Laplacian of phi x equals 0 in that ball, and on the boundary, phi agrees with a shifted version of the fundamental solution. So phi of y minus x, again, x is fixed on the boundary. So again, just to reiterate, we have this ball, okay, and inside of that ball, phi is harmonic. And on the boundary, okay, like on here, we get that phi is just, again, a shifted version of the fundamental solution. And it turns out the beautiful thing is we can actually find an explicit formula for phi x, and therefore you'll see an explicit formula for our solution, which will ultimately lead to what's called the Poisson equation on the ball and to what's called the Poisson kernel on the ball. Okay, and again, here's a super neat idea that again makes this work, because you see this fundamental solution, phi x, that has a singularity at the origin. It blows up at 0. So if you shift phi, it has a singularity at x. So phi of y minus x has a singularity at x. At x. Okay. So again, for the ball, if we have this ball and this point x here, well, we know this point is bad. So what we would like to do, we would like to reflect it out. So kind of move it out of the ball, because we like that ball and we have this kind of bad point, kind of this singularity. So we kind of want to move it out to what's called x bar. And let's see how we can do that. There's actually a very easy way of doing that, because if you take x, okay, if you divide this by the length of x, that doesn't quite work, because x over length of x, it would still be on the unit ball or the unit sphere. And therefore, to even push it out further, we divide it by the length of x squared. Because remember, the length of x is less than 1. So this length will have length greater than 1, so outside of the ball. And again, just to reiterate, length of x bar, what this becomes, it's length of x over length of x squared, which is 1 over length of x, which is bigger than 1. So definitely this x bar, it's outside of the unit ball. And therefore, what we would like to do, so here's our here's our guess for a solution. Let's let our helper function phi x of y simply be the following. So you take the fundamental solution at y, and then you shift it by x bar, so that again, the bad point comes out, and you just stretch it by the length of x. You'll see why. It's in order to get this agreement. Okay, and this is, again, our candidate for the solution. And now all we need to show is that this ansatz, this guess, solves this PDE. So we need to show that phi x is harmonic and it agrees with the fundamental solution. To show that it's harmonic, it's just an exercise in the Chen-Lu. So differentiate this with respect to y and use phi as harmonic. So that's not a problem. It's the other thing that's a bit harder to show. So show that if you have some point y on the boundary, then phi xy equals phi of, I believe, y minus x. And for this, we just need a couple of, we need just a couple of calculations, but I would like to remind you what is phi of this thing, absolute value of x times y minus x bar. Again, that is some constant over the absolute value of this. So absolute value of x, absolute value of y minus x to the n minus 2. So let's focus on this expression, x times y minus x bar. And it turns out, in the case of the unit sphere, we can actually simplify this. And for this, just a very nice, almost multivariable calculus calculation. So take this length, and again, just for the fun of it, let's square this. So it's a positive thing, so let's square, and then we get length of x squared, and then y minus length of x squared. And this thing, we can expand this out as a dot product. So x squared, and then almost like the expanding a minus b squared out. This is length of y squared minus 2 times y dotted with this reflected version of x plus the reflected version of x squared. But then this is again length of x squared. Now, y is on the unit sphere, so this is 1. And then minus 2, y dotted with, again, the definition is x over length of x squared, by definition of x bar. And this we calculated, it's 1 over length of x squared. Okay, but the nice thing is, if you distribute this, this becomes length of x squared minus 2y dotted with, again, those two things cancel out, y dotted with x plus 1. And then it turns out, again, length of y is 1. So this becomes x squared minus 2y dotted with x, or if you want, x dotted with y, plus length of y squared. And again, by the reverse of this, this becomes length of x. This becomes length of x minus y squared. So what do we get? We get that the square of this equals to the square of this, and therefore those two things are equal. So length of x times y minus x bar is just length of x minus y. And again, why is that useful? Because what was this helper function? That is just phi of absolute value of x and then y minus x bar. And that becomes, again, 1 over some constant, 1 over length of x, length of y minus x bar to the n minus 2. But we've just shown that this simplifies. So this becomes 1 over c times 1 over x minus y to the n minus 2. But this is precisely the fundamental solution as y minus x. So again, just to reiterate, and if this works, what we wanted to show, I know it was quite a lengthy calculation, we wanted to show that on the boundary, phi x equals to the fundamental solution. We used the fact the fundamental solution had this form, and it turns out with this calculation, this simplifies to basically length of x minus y. And that's precisely what we need for to get this simplification. And also remember, the fundamental solution is symmetric. That's why we actually have that. All right. And again, that's very good. We found our helper function. And then next step, again, in the Green's function. What is the Green's function? By definition, it is just the fundamental solution minus our helper function. So think like our corrector term. And so in this case, explicit version of the Green's function is phi of y minus x minus phi of absolute value of x and then y minus x bar. Kind of like that. Again, which is amazing because in practice, Green's functions are hard to find. But now we do have this explicit formula, and using that, we can actually write u in terms of our Green's function. So u of x, by definition, or not by definition, but a result that I've proven in another video, it becomes minus the integral over the sphere of our initial, of our boundary condition. Remember, Laplace, u was g on the boundary, times the normal derivative of this, x comma y, over the thing. So this is our explicit representation of the function u in terms of our Green's function. But I would like to remind you, we are on the unit sphere, where the normal derivative is very easy to find. Namely, if you're at the point y, the normal vector is just y over length of y, but this time on the unit sphere, this just becomes y. So in that case, what we get, the normal derivative is just the gradient dotted with just y, and then again, ds of y. And therefore, all we need to do now is to find that gradient and then dot it, and then we get our explicit formula. All right, so step 4. So let's calculate. Let's say for every index, let's calculate kind of the ith derivative of g. So that becomes, again, by definition, g was phi of y minus x minus phi of this gibberish. So phi of length of x, y minus x bar with respect to yi. And so, again, using the Chen-Lu, we get two things. So this becomes phi, the ith derivative of phi, minus this huge thing, which we'll calculate now in a second. So we have two terms. So this is A, and this is B. And just like we do in PDEs, we'll just study each term separately. So now I would like to remind you, and this is where we need our constant, phi of x is 1 over n times n minus 2 alpha n. 1 over x to the n minus 2. And by the way, I mean, I stated like that. It's after you learn it 100 times that you finally know the formula. Okay. So you'll be able to do it with such elegance as well one day. And then phi of yi, so the ith derivative of this, again, we still have our constants, n times n minus 2 alpha n. And then this thing you just write as x to the 2 minus n. So by the Chen-Lu, this becomes 2 minus n x to the 1 minus n times the derivative of absolute value, which becomes, in this case, xi over length of x. So this kind of cancels out, and this cancels out with a minus 1. All right, and then after this simplification, what we simply get, I believe, minus xi over n alpha n length of x to the n. So this is the derivative of phi yi, and we can use that to now calculate our two terms, a and b. And notice a, what it is just this, but you replace x by y minus x. So for part A, and by the way, now we're finally on page 3 out of 4 of my notes. So we get phi yi of y minus x equals, I believe, so yi minus xi. So, but with the minus, this becomes xi minus yi over n alpha n to the length of x minus y to the n, just by symmetry. So that was the first part. And then the second part here, where we have to do a Chen-Lu extravaganza. So phi of length of x, y minus x bar, again, with respect to yi. And again, by the Chen-Lu, this becomes phi yi times length of x, y minus x bar, times the derivative of this, what I believe is just becomes length of x. And then by the formula above, what this becomes, so it's minus length of x, then yi minus, so x bar, which remember in this case is xi over length of x squared times length of x over n alpha n, again, length of x times y minus x bar squared. And again, I'm sorry for all this horrible math, but it does simplify quite nicely, because here we have length of x, and that simplifies with length of x squared. But then this becomes just like I wrote this in color, so minus yi length of x squared, and then this x squared cancels out with here, so minus xi over n alpha n. And then for this one, remember at the very beginning, I actually told you this simplifies quite nicely. That's when you use, this factor, what a minus b squared. And we found that this is just x minus y to the nth power. So indeed, that derivative in the end doesn't look too bad. And therefore, the terms a and b simplify quite nicely, and we can calculate our derivative gyi of xy to simply be, remember there was a minus b, and therefore what we get, so we do have this common factor of n alpha n x minus y to the n. Now from a, we actually got, if you review this, we got xi minus yi, and then minus minus becomes plus. So plus yi x squared minus xi. So you see, the beautiful thing is this actually cancels out, and we can factor out we can factor out yi. So this becomes 1 over n alpha n x minus y to the n times x squared minus 1 times yi. And that's the thing, by the way, about PDEs. So the calculations are crazy, but also kind of meditative. And in fact, they also simplify quite nicely. So we do have all these yi's, but then you'll see in the end, we get something absolutely beautiful, because what have we done? So just a little recap. So what we needed is u of x. We had this representation formula in terms of the gradient And then we calculated the ith component of the gradient, that is a minus b. And after all this calculation, we finally calculated the gradient. So all we need to do now is just calculate this normal derivative. So dot the gradient with y. And you'll see again, there's a beautiful simplification. Well, it's quite long, but I think it's very important. I don't know how many people are watching, but I hope for the people who are watching, you find that useful. Because I always super confused about this, and hopefully now it becomes a little bit clearer. So dg dotted with y. So it's almost dj Peyam in the house, but dg Peyam in the house. And so by definition, this is the sum from I from 1 to n of g of yi times yi. And that is the sum from I from 1 to n of, again, we found this explicitly, so length of x squared minus 1 times yi over n alpha n, length of x minus y to the n times yi. And now we get this common factor here that just pops out. So almost, it's the factor except for the yi. Kind of like this. Yeah, kind of, okay. Kind of, okay. And then this pops out of the sum, so we get, and again, you'll see the yi's magically disappear. So it's length of x squared minus 1 over n alpha n, x minus y to the n times, so sum for I to 1 of yi squared. But now here's something you forgot. So this is the length of y squared. But remember, y was on the boundary. So of the boundary of the unit circle. So this is 1. And in the end, the normal derivative just becomes this. All right. And then we're almost done, pretty much. So step 5. So again, that was the normal derivative. I hope this recorded. Okay, and then u of x then becomes the minus, a representation formula, minus integral over the sphere of g of y. Again, what's called the normal derivative of g over that sphere. But now remember, we found the normal derivative, so this becomes minus integral over the sphere, g of y, length of x squared minus 1 over n alpha n. I don't know why this became Laplacian, but over n alpha n x minus y minus y to the n ds of y. All right, and then again, anything that doesn't depend on y, you can just pull this out. And we also get, this cancels out with the minus. And last but not least, finally, we get that u of x equals 1 minus x to the n over n alpha n integral over the sphere of g of y over x minus y to the n times ds of y. And lo and behold, this is our explicit formula for the solution of, again, Laplace's equation on the ball. So minus Laplacian u equals 0 in the open ball and u equals g on the sphere. And not only that, the beautiful thing is we can easily, using a change of variables, also solve the equation on any ball of radius r. So I'm not gonna do it, I'm just gonna mention it. So if you solve Laplacian of u equals 0 in B0r, and then u equals g on the units, not the unit sphere, but the what's called the sphere of radius 0, sorry, of centered at 0 and radius r, then there's just a little clever trick, because if you let u bar of x be u of rx, so if you compress this, then in fact you can show that minus Laplacian of u bar equals 0, but in, again, the compressed unit ball, so just a unit ball in this case, and then u bar equals g bar on the unit ball, okay, where g bar is g of rx. And then the point is, you then find that u bar is your usual Poisson's formula, and then using the change of variables, you ultimately get that u of x is r squared minus length of x squared over Rn alpha n integral over the sphere of g of y, well, I think I already used, no, g of y over x minus y to the n ds of y. And this is the celebrated Poisson's formula for the ball. Again, fish formula for ball. So last time I did the Poisson formula for the half plane, and now we did it on the ball. And again, if you do physics, you may recognize this as a potential. And in fact, this is also a convolution. And also, by the way, this term r squared minus length of x squared over n alpha n times r, and then 1 over x minus y to the n, what that's called, that's the Poisson kernel for the ball. All right. And I hope you like this PDE extravaganza. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.